a couple other areas where we don't have any.
Everybody mind if I go ahead and get started? A few people may jump in, but that's okay. If they do jump in, I'll try not to go back and restart. So I'll give you the privilege of being here first. My name's Troy. I'm with a company called Spectrum Environmental Solutions. We do a variety of interesting, fun things. We try to keep it fun. I'm wanting to talk about something that we've been working at doing for a very long time. And I'm going to show you why there are some hurdles along the way. But then I want to show you the value of how it works. A little bit of high picture. I'm going to try to stay away from the spectroscopy and the math. This is a very mathematics intensive software that we developed, and I'm going to try to stay away from that to keep it practical, if that's okay. Basically, this is an EPA method. This is an EPA approved method for determining mass. So that's different than just the open path concentration, path integrated concentration. Concentrations are interesting. Those are compared against health-based limits and effect screening levels and other things for concentration, yes or no, pass, fail. But if you want to do permitting people do not live in a world of concentrations. They live in a world of mass, tons per year, pounds per hour. And there's some interesting ways to use this path integrated concentration and turn it into mass. And there is an EPA method for it. I just want to go over some of that history and a little bit about what we did to move this forward. I'm subject to moving forward. Clicker's dead. Page down. Down. All right, Brian.
There you go.
Sir. No idea. It was working 2 seconds ago,
There we
everybody.
go. That's working.
That
These the two side buttons.
Righty. There we go. So quickly, a little bit about Spectrum. We do a variety of things. It's true, we are a device manufacturer. We build devices, open path, extractive, variety of different optical devices. We build them and the software to operate the systems. We also do a fair bit of consulting work, and that consulting entails, most people know us for our flare work, but we also do quite a bit of fence line, hazardous waste combustion, instrumentation reviews. Many people don't know it, but I like to play in this unique world of dispersion modeling, not air mod, not permit modeling, but unique event modeling. Events from flares are uniquely interesting to me, but also other types of trajectory, backward trajectory modeling, and some other interesting things. Our monitoring group uses our equipment and everybody else's equipment to do a whole variety of studies, mostly in the FTIR UV world, but also using other devices, usually weird, strange, and unusual things. So we're not a stack testing company like Alliance. We don't necessarily go out there and stack test routinely, but we do apply our FTIR extractive devices to source testing. So we kind of come along as a specialty sub in that manner. And then the other part of the company is all engineered systems. This is our long-term design to run 24/7, integrated shelters, integrated data management, power management, communications, pushing everything to the website. So the engineered systems, again, incorporate a lot of our equipment, but also a lot of other people's equipment as well. So today I want to talk about something that's that we don't talk about a whole lot, and that's these two pieces. This thing called Radial Plume mapping, and this other part of emissions Flux. So it's kind of a fun overlap. It's a unique application of open path technology. This is not brand new. This has been around for quite some time. The EPA method is other test method, OTM-10, came out in 2006. And the It is based on a patent by a guy who's actually here at the conference, Dr. Ram Hashmane. I think he's around here somewhere, speaking in other settings, speaking right now on Opgal. So he's working with Opgal at the moment. This is his patent. He and Dr. Yost at Washington University developed this back in the late 90s for his PhD. And it's actually quite fascinating. I've had a curious interest in this for way too long, a long time. I think it has huge opportunities to validate the proof to demonstrate that our emission factors that we use for permitting and emissions inventory are actually close to correct. Sometimes they may not be. The other thing is that it's been updated and incorporated into the handbook. Some of you have seen flipped through the 2018 is the most recent update of the EPA handbook for optical remote sensing. It lists 7 or 8 different technologies in there, of which OpenPath, FTIR, UV, TDL, all of those are in there. And this is referenced in its own separate section. So OTM-10 Flux measurement. And here's a couple examples I stole from other studies long ago. You can do a horizontal radial plume mapping, put the analyzer down in the bottom corner, place a whole bunch of mirrors, spread all out all over the facility, do a little measurement, cycling through all those mirrors, and you come up with this type of tomography that lays out for you with the software, with the mathematics, where the hot spots could be. And you can see quickly that this could be a very powerful technique if you have a site where you're not sure where the emissions are. Or the EPA used this technique a lot for landfills. And you can imagine the amount of methane gas leaking through covers, land covers over the fill. Where are the weak spots in the landfill? So looking for methane and H2S from landfill gas is probably where EPA applied this technique the most. Here they were thinking of spending a gazillion dollars to cap and cover those 2 wastewater open top tanks. And in the end, they realized that that's not the major source of emissions. It was the filter house, the sludge filter building, and they actually had a leak from a vessel they thought was already covered. So interesting technique and could be used. Here's the application doing it vertically. So this is using a crosswind, and you could have an area fugitive source upwind. The wind blows through it. You basically create this cool little triangular approach, and you calculate the flux going through that zone. This is a bivariate Gaussian calculation, just Gaussian dispersion technique on the bottom, between the bottom row, and then the same thing vertically. You overlap the 2 bivariate Gaussian equations together, and can come up with a pretty cool estimate of the wind flow and the mass flow. Here's an example at an agricultural site. This goes way back into the 90s. I forget who, late 90s, early 2000s. This was done by Arcadis. Put the van over here, little man jack some distance away, and you can see the path, basically how the system would work. And it would just scan through once a minute, every path, and the auto tracker would move the beam, move the device. And within 5 minutes or 6 minutes, you would capture the data set for that one point in time. This is kind of what the output would look like. You can see the FTIR would be sitting down at the corner. There'd be a series of mirrors, as you saw in the photo, a series of elevated mirrors, maybe 1 or 2 mirrors behind. I guess the easiest way for me to visualize this is pretend you're standing looking into the wind and the source is behind you, and this is the plane in front of you, and this is the plume as it approaches your face as you're looking at this thing, right? And the mathematics are such that you can actually start to calculate what is that vertical profile, because we know the concentration at the ground is not the same at the midpoint, not the same at the top. The wind is pushing this thing to you. So you can see it has some appeal for doing a mass measurement. It's not necessarily the right technique if you're doing hot gases from a boiler or an incinerator or something else. Hot gases are going to keep lifting and going higher and higher and higher. So it is, limited to your project scope, your design of experiment. So you have to think about some of these things. But it is kind of a cool idea, and it had problems. I mean, the most obvious problem that we had since 2002 or 2003, when the patent was issued, is that it's patented. The radial plume mapping technique had a patent at the University of Washington with Michael Yost and Ram Hashmoneh. There was a fee required to use it, and it was based on a per test event. It was a very oddly worded patent license agreement. And there is no commercial RPM software available because of it. So they basically said, there's a technique, it's complicated math, here's some papers on it, good luck. There's no software. It's not like you call the University of Washington and they email you a disk and they give you the package. Because of that, and the patent, it basically sat on the desk of the EPA for the last 20 years until the patent finally expired in 2018. So because of that, very limited use, mostly in tanks, some tank farm emissions tests that Ram Hashmoneh performed himself in other countries. And in the agricultural world, we see quite a few papers done by the US Department of Agriculture. Some of these people never acquired the patent, never gave attribution to the patent in their public papers. Most of those are international papers, but very few papers are on this topic. And therefore, the agency folks, even at the agency level, state by state level, most of them don't even know this exists. But now that it's expired, great minds like to use things that have promise. And our team thought that this would be a spectacular tool to put in our toolbox. And our new software does the bivariate fit. There's a ton of statistical validation techniques that go into this technique. Basically, how well does the actual data fit using this concordance correlation factor. If the CCF is not proper, if it's actually not a Gaussian fit, that usually means wind moved dramatically in the 5-minute period. And instead of giving a nice view of the plume coming at you, it's all messed up, right? The wind moves around. You probably had too long of an analytical time, or other things, of course, could have happened. Our system accommodates multiple paths, multiple variable configurations, just about any analyzer you want to put on it that has a digital output. So we could accommodate the FTIR, UV, TDL, and obviously others. It can accommodate the 2 wind sensors. The method talks about having 2 wind sonic anemometers, one at ground level and one at the height of the highest mirror. And it basically assumes wind is consistent across the entire x-axis. That's the assumption in the method. And then there's an interpolation from low to high. So as every meter block or so you go up in height, the EPA method, the OTM-10, basically assume that. We don't like that idea. We think the wind field is just as important as the concentration field. So the wind field needs to have a lot more variability. So we've incorporated significantly more wind sensors to come up with a wind field determination instead of these assumptions. And then we validated this against a variety of historical data sets. There are data sets in a variety of papers, not many papers, but some papers. We plug in the same numbers that they plugged in, and we try to get the same result that they got. And actually, when you're using data sets from a published paper, there's a lot of things people sometimes don't put in their published paper, where they may say, oh, this was 2 meters and 10 meters off the ground. But in the text of the methodology, they say, actually, it was 1.6 meters off the ground, and the high mirror was only 8 meters off the ground. So adjusting how they actually represented their test method can be important. And here's the example. This is just for fun to give you a visualization. We do it on a 1 meter by 1 meter grid. Inside each 1 meter cell, we use a variety of the wind information that we're collecting, concentrate all the different paths, 5 different paths, and we do the mathematics to fit these Gaussian and this is basically the shape you get down here. I tried to find exactly that date to match this date, but I couldn't find that one in my data set, so sorry for that. But the two are close enough to give you the impression, at least, that there is a methodology here, meter by meter grid, on how we do this. Here's our site. So we did this last fall. It's a very complex, very tight, small facility. They had an issue. It's a batch operation, wild and variable wastewater contributions, just what you would imagine at a batch site. A lot of concentrations of wastewater samples that they would go out and grab. They never correlated their grab sampling with what their actual operators are doing at the time. Wickedly wild, crazy numbers. There's a couple of interesting pits, the red pit, the white pit, a pit up here, and another one down in here. This one's actually underneath a part of the roof. This little corner is a lean-to shed. So odd pits, strange sizes, small, compact, limited distances. You can already imagine the wind profile inside of a facility is absolutely nothing like the wind at the airport, big open wild field. So, and obviously smaller distances, barely 30 feet in some cases. So the idea was to estimate the emissions from their wastewater activities. They use exactly what most every chemical plant in the country uses, Water 9, a version of the old EPA software, Water 9, or the new version of the Hygromantis ToxChem. And you plug in all your numbers and you come up with these wild, crazy numbers. And the numbers for this case were through the roof based on ToxChem. So very, very large potential to emit. So much so that the site would no longer be a synthetic miner site. And so it could have triggered a large number of things permitting-wise for the facility, not just permitting-wise, but also expensive and extensive controls, re-looking at all of their ACTs and all kinds of other costs, if you can well imagine. So the idea was to validate the ToxChem numbers, validate at least order of magnitude. Are these emission estimates from the software packages even close to what we're seeing at these four pits? I'm going to zoom in here. This is the red and the white pit, a little bit closer in. There's a light natural wind. It's an area with rather hilly. They have large periods of time with stagnant wind, very, very low movement of wind. This is a 5-foot berm that surrounds these two pits in particular. And we wanted to know the wastewater emissions from this versus this separately, because the contributions to each pit are quite variable and quite different. How do we accommodate for downwash? How do we accommodate for the wind? Can we induce an artificial wind and increase the wind flows to get us above the 0.25 meter per second lower threshold, the most sonic anemometers, which is what we did. So the goal was to come up with a modified met wind approach and use the radial plume mapping algorithms. We got this approved by the agency. They agreed to implement this. There's a couple of reasons why that was so readily agreeable. Number one, it's near a facility. The facility is near Washington University, which is where Michael Yost still teaches to this day. So it's in that part of the country. So there was still some name recognition and the method and the technique. So the agency was willing to give this a go. The idea was to set up 5 mirrors at a variety of distances and 2 at the height and a minimum of 3 sonic anemometers. I think I already mentioned that we had a high stagnant wind. So we installed these 3 small fans. Basically, if you can imagine 3 small fans at this point, they were directed towards the center point of the view. And the idea is to create a gentle breeze. We don't want white caps showing up on the surface of the water. We're not trying to flush or scrub any of the emissions off the water. It was just to keep us above that 0.25 meter per second. And we still wanted to feel the influence of natural wind when the natural wind did occur. And so which should be evident when you start seeing the plume profile move and shift and bounce around every 5 minutes. So if we got to the point where for an hour, the wind was always in one point and the plume shape was always in the center point, then we knew we were sending so much wind that we were overpowering the natural wind. If that makes sense. And then, of course, our goal was to sustain the sum squared errors for the two Gaussian fits. The method talks about doing this sequentially. You have to sum square errors for the Gaussian fit on the x-axis first and then the vertical. So getting the software to do it in order actually did make a difference. So I'm not sure mathematically why. Rom must have figured that out in the course of his studies too. So that is in the method. And then the concordance correlation factor, 80%. It had to be at least within 80% of what a true Gaussian fit would suggest. And if not, you just throw that 5-minute data set out. So here's basically what it looks like if miracles happen, and I can start the video, but they put me into this mode here where I'm not sure I can get it to play. And I told them that this would happen. Is it moving? So every 5 minutes, you'll get you should get a different visualization of how that plane, how that emission would change and move. This one would probably get thrown out by the CCF. This one we probably would keep. And what it does is it provides, of course, based on the actual wind speed, the wind direction was shifting this along the x-axis, but we get a new emission rate for that 5-minute period of time. And then over the course of however many hours or days we ran the study for this particular point, you start summing up Simpson's integration, right? You start summing up all of these 5-minute blocks. While this was going on with the analytical and the wind, another group was doing what you would imagine you're doing at a batch plant, and that's all the operator interviews. So we came up with a detailed log of every time operators turned just about every valve, every scrubber discharge, every truck of methanol, a rail car of methanol that would show up, boiler blowdown events, cooling tower blowdown events, hosing and cleaning out various batch reactors. How long did that take? Where did that water go? Into which pit? So it actually was a quite extensive interview activities being performed, and they did grab some water samples along the way, and it was actually a quite interesting project. Here's the result now over time. This is an 8-hour period. Sorry, this is one day from about 3 in the afternoon to about midnight. We varied the time to coincide with the operator, so not everything happened between 7 and 4. We wanted to see what they were doing in the evenings and the off hours as well. And with each one of these major events throughout that day, they're linked and they're correlated to a human activity. Some human event is occurring in this batch operation. This happens to be for methanol. That's one of the HAPs, yeah. We actually look for several others as well, but I'm showing you the methanol one because it's most innocuous. All 4 wastewater subs had a totally different, unique profile. Not only that, but we altered the study. A low methanol a day, option 1, low methanol option 2. There's various things and techniques that the operators would do under various days. It took a while for them to talk and communicate and hear what they do and how they do it and when they do it. And we wanted to make sure we were analyzing the period before, during, and after each one of these unique events. And from that, you can well imagine all the good conversations that go on that say, if you ran day 1 every day for your entire year, it's barely 0.3 tons per year of emissions. But if you ran in mode, the second mode here, there's 10, 11 tons per year on day 7. So if historically, when you went out there and grabbed a sample and threw it into ToxChem would think, oh, that's the number. And they just got done discharging your scrubber water from unloading a rail car of methanol. That's a very high methanol number. If you use that number in ToxChem, you came up with a ginormous number for your total emissions. So what this was able to do was show that based on their activities and how they do what they do and the emissions during their actual events that they do in the plant, they think they can, hold on to their synthetic miner status, which is hooray, good for them. The agency is now reviewing their revised permit application. So, however, you can also imagine if they start doing things differently. So instead of getting a permit now based on just maximum potential to emit, they're going to get a permit with some operational criteria. How many rail cars, how often, what are you doing concurrently? What activities are occurring at the same time in the unit that you ought not to be doing at the same time? You should spread these out. And they have 4 different main sumps they could go to. Some idea was to put different things in different sumps. The boiler blowdown is a little warm. So that water hits any one of these pits, that boiler blowdown water is going to do what to whatever volatiles may be in the water? All of it's gone. So redirecting, maybe cooling, maybe putting the boiler blowdown in a separate pit, letting it cool down, and then letting it flow into the city discharge pit. All of those little operational things are very insightful, very fun things to talk about, and engineers, at least I do, I enjoy hitting on all those operational improvements to help them manage their emissions in a much better way. Huge, yeah, wild swings in how they manage flow rates from the different sumps and their contributions. Differences between operators. Some operators would stand there for 30 minutes and hose down the prior batch reactor, clean everything out, the top, the bottom, the inside, the floor, everything. Other operators would clean it out in 5 minutes. So low flow, but high concentration. And they would probably leave some methanol and formaldehyde and phenol and some other things behind, right? So being able to say that's the same activity, but wildly different numbers. Now that's an operator comparison. Let's talk about how that happened. But fun stuff. I think this was good. We learned a lot. The model is really fascinating. It's embedded now into our New Wave software package, so we can certainly do these a lot more. There's a lot of complex math that now that we got that under wraps, I think that helps a lot. We definitely learned some things are more movable in the data set than others. Some things really make a difference. Other aspects, maybe not so critical. Knowing the wind is amazingly critical in a tight space. All the other historical studies that are in the literature are giant, large, open agricultural fields, lagoons, wastewater pits that are ginormous. Here, we're doing very tight space. Definitely did the digital data set comparisons with all the available literature. Our numbers match up very well, less than 10% variation between our results and the paper's result. We have not done an in-field staged release. That would be fun to do. I'd like to find a place to do that and actually put something unique like an SF6 or something that's a nice marker or something that we can see is unique and do a controlled release and validate. That is a data set that EPA did back in 2005. They did a controlled release at Duke University, the Duke Forest is what it's called, the Duke Forest study. So we replicated the Duke Forest data set and came up with actually a better number than what ROM had at Arcadis back then, because we found we think they made some errors in their math. The other part that's interesting is this whole ToxChem Water 9 model stuff. Somebody needs to get a larger data set of this. A lot of people rely on ToxChem, not just for their emissions inventory, but also for their permitting potential to emit. And we played with Water 9 a little bit. We played a lot more with ToxChem. And ToxChem is a steady state model. It's an annualized steady state. It uses the net data from a local airport, hourly emissions type of thing you would do if you were doing air mod or anything. But both emission models were significantly divergent from our results. And so that raises a huge number of questions. Is the technique, the radial plume mapping technique, that bad? I don't think so. Is the model off? It has to be off. And there's a whole bunch of reasons for why it could be off. using high concentrations, using longer durations, using liquid water temperatures, steady state numbers. These are kind of equations of state that ToxChem uses. So they don't take into consideration all of the operational pieces going on. I think it'd be fun to do some type of a simulation of all these operational modes. What the plant did so far is just estimating the number of times a year certain things occur. How many times certain reactors are washed. A certain time rail cars are loaded and unloaded. So rather than that, trying to come up with some a little bit better sensitivity, confidence on what's that true. And I hate to use this word PTE, potential to emit, because in the permitting world, potential to emit is your worst case potential to emit. And that's not what, nobody wants to permit the worst case. People want to permit the likely case. So really, what is the likely case for their actual emissions throughout a year? And there's tons of work to do on new operational modes, things that they can tidy up and do things a whole lot better and improve their plan. So this was a unique application of FTIR. It's not just suitable for fence line monitoring. It can be used for Flux, and there is now a way to do that. Now that the patent has expired, it's now open free range. So everyone can go out there and try to build this software if you want to attempt. It's not impossible. It did take us a considerable bit of time to work out some of the details. Some of the older versions that were run by a company called Arcadis, that was the contractor for US EPA. That contractor for US EPA is no longer EPA's contractor. And therefore, if you try to do a FOIA request, and not that anyone would think of that, do a FOIA request and ask EPA for a copy of RPM. They won't give it to you because nobody can find it. Trust me, I already tried. You can try again if you want to. But nobody has a copy of this, and Arcadis doesn't do this kind of work anymore. And all the people who did this type of work for Arcadis are no longer with Arcadis. So actually, if you ask me who else has an RPM model that they could put to use, there's probably less than 4 people in the universe who probably have a software on the shelf that might need to be touched or tweaked or adjusted. But who are actually in a position to maybe do some of these. It's not so many anymore. Other than us, you can always think of us. We're here.